Here in Enrichment Example 4.1, we're going to extend the ideas of the joint model and show its connection to a Bayesian model, and in particular introduce the concept of probability trees. That particular graphical device leading to calculations of probabilities of joint outcomes is one that's very useful in decision modeling. And you might not use it per se, but what it will do is actually create the construct from which other ideas will be developed along the way. Probability trees are also used in some sense, especially when you get into fuzzy set theory, which is also a way to process now qualitative information, but do so in a quantitative kind of fashion. And how do you put those rules together? And that's something that gets used quite a bit in certain kinds of decision-making models that are out there. So let's get in this in the same kind of context as what we were talking about before, and that's really about a test reliability, but particularly now what you might call it really an updating situation. The context here is going to be about concrete strengths, but it could be about any property that we might be testing of any material or any other kind of process, really. We're going to let x, a random variable, be the true strength of the concrete specimen. That would be the compressive strength. And for simplicity in our example, we're going to let it have only 3 possible outcomes: 2, 3, and 4, and this would have units of kips per square inch, or KSI. And then what happens is that we go out and we take samples, oftentimes from a ready mix machine coming right out of the concrete mixer, and form cylinders. The size of the cylinder will vary. It used to be the traditional size for the core was a 6-inch diameter, 12 inches long. Now it's common to do 4x8s, and sometimes there are 3x6s and that sort of thing. And if you're actually going to go out and do a physical core as opposed to casting a cylinder, then those might be actually quite a bit smaller, on the smaller side as compared to that 6x12 or even 4x8. Right? And so y is going to be our observed strength from the test core or from the test cylinder. And those two will lump or discretize as having possible outcomes of 2, 3, and 4 KSI. And sort of our given here from our best experience before testing tells us that our marginal distribution of x, our true strengths, is going to be 0.3, 0.6, 0.1 for x equal to 2, 3, and 4 respectively. And so that's using this particular design mix of concrete. We mix it up, and 30% chance that its true strength is 2 KSI, 60% chance that it's 3 KSI, and 0.1 or 10% chance that it's 4 KSI. So that's our first item that we have, and what we're really asking here is how reliable is the test. That's similar to what we were asking about before in one of the other illustrations, and that is that we go and we test it, and the tested strength is reasonably close to the given or the actual strength. Right? other pieces of information here that we might have typically in this problem are, say, conditional information about the test values. And so here on this vertical axis we'll have the possible y values 2, 3, and 4, and then across the top we'll have a conditional distribution. The probability of y given x is a particular value. Right, so for a fixed value, a true strength of 2 KSI, we found from prior experience that we have a 70% chance that our test value is going to also be 2. And if x is equal to 2, we have a 30% chance that our test is actually going to indicate that it's a little bit stronger than that. And then we have a 0 chance, given that we have a 2,000 PSI concrete, that our test is going to say that it's up around 4 KSI. Right? If the true strength is 3, given that it is, then there's a 20% chance that the test will indicate that it's weaker, 60% that it's correct, and 20% up high. And then out here in this last one we have, if the true strength is 4, we have no chance that the test will show that it's 2, and then we have 0.3 and 0.7. Those are our final numbers there. Right? And note that the sum of our conditional probabilities, okay, for this is now the x value is fixed. Right, so if we sum over all the y's, right, so that means in our table, if we sum over all those, note that those in each case we have 1.0 in each one of those. Right, so there's a couple of different kinds of questions that we might ultimately be asking here. One of them is, what's the marginal distribution of y, say before the test? And going back to that question I posed before about the reliability, what's the probability that the test is in error? Or another way to write that mathematically is that the true strength and the observed strength are not equal to each other. And there's a variety of ways that you could begin to approach this, but partly to illustrate a concept that extends our thinking and our tools available to us. I'm going to introduce this in the context of probability trees. Now, your authors, Montgomery and Runger, actually introduced the idea of trees way back in the introductory sections, chapters 1 and 2, as they were trying to get you to think about developing different probability spaces and that sample space and the different outcomes of random events. Here we're going to do it in the context of how you might actually perform a calculation. Now, one thing about probability trees is that you oftentimes need a lot of space on the page. So I'm going to end up using about half the space on this particular page, all the way from the top here down to the bottom, and put my first node down here. And we're just going to do branches or trees like a tree that looks like branches on a tree, where the first thing we're going to do is actually look at 3 different possibilities that are associated with x equal to 2, x equal to 3, and x equal to 4. And there's a lot of different styles for how to do this. I'm not going to suggest any formal style. Rather, when you get into these in a decision analysis class, they'll approach a very more specific way that you want to label these things, that sort of thing. I'm going to put here just in a different color the probability that we walk down any one of these branches. So we know from our original given data that we had a 30% chance the true strength was 2. We had 60% chance that it was 3, and only 10% chance the true strength was 4. Now, branching off from any one of those, we have 3 possible outcomes for y, right, our observed test. So this is why it gets kind of tricky when you draw these things, because if you don't plan them out ahead of time, you end up with not enough space. And even here, as I've tried to be very careful about it, I'm going to end up squeezing information. It's just very common and typical to do these. And so if you want really nice publishable quality probability trees, then you really probably have to do these a couple of times before you get them laid out in a nice, really pretty fashion. Right. Now, because this probability tree only has 2 levels to it, it'll make it a little bit easier to write out some of the information. I'm going to stick the possible y values here to the right rather than right on the branch itself. And again, that's really just conserve some space. And it is somewhat repetitive, and some people won't bother when they're just sketching this out to repeat all this information. You really should have it, but you know, sometimes you'll take shortcuts, and sometimes when you take shortcuts you make mistakes as a result. But I'm going to slide this back up so we can see this table, because this will also illustrate the notion of this conditional information that we were given to us before. And that is that given that x is equal to 2, the odds that we have an observed test of 2, 3, or 4 are given to us in this table. So there's our 0.7, 0.3, and then 0. And then likewise 0.2, 0.6, 0.2, and then down below we have, given that x is equal to 4, we have 0, 0.3, and 0.7. Right? All seems well, fine, and good, but why? What are we after here? Well, remember one of our questions was, what's the marginal probability of y? Right? And we can start to get at that by actually looking at the probability of joint outcomes. So, for instance, the probability that x is equal to 2 and y is equal to 2 is now just the product of the probabilities that are on that tree. So 0.3 times 0.7 is going to be 0.21, so 21% chance. Right, remember that the marginal could be reworked here in all kinds of ways, right? Remember we had that relationship between joint, conditional, and marginal, that a marginal of y was equal to a conditional of y on x times the x value. Right? And joint values, remember, and when we did that we had to sum over all the x to get there. Right? The joint distribution of x and y was equal to the product of the marginals if independent. Right? Well, we don't suspect independence here, so that's not a very useful sort of result. And of course the one you were waiting for is, hey, the joint is equal to the conditional times the marginal for a specific value. Right, so that's why we were able to take this x equal to 2, y equal to, join information, and here's the marginal of x times the conditional of y given a specific x value, bam. And that gives us one of them. And of course we can then do all our other combinations. And I will do one more live, and then I'll just write them all down, and then you can follow likewise. Set up perfect. And so through the magic of pause and restarting, you'll see the rest of these values as worked out through here. Right now, how does that get us closer to what we really want? We wanted the marginal of y, right? And now we have mutually exclusive sets of events, right? And so we can come back through, and actually what we're going to do is just simply work through versions of these up here, and really specifically this one, that for probability that y is equal to 2, right, we sum up just those combinations with y equal to 2. We have a 0.21, we have a 0.12, and a 0. Right, so that would be 0.21 plus 0.12 equals 0.33. And then for y equal to 3, and we have 0.09 plus 0.36 plus 0.03, or 0.48. And then for the last one, we'll have y equal to 4. We could take 1 minus these two, right? Or we can do the same thing, add up 0.07, 0.12, and the 0, and we should get 0.19. Of course, add up those three, and they should be equal to 1. And they do. So that's good. Notice also, if we were to sum up all the joint probabilities, those would also equal to 1, as they should. Right? So that gives us the marginal likelihood of y, that when we go and do the test, that our likelihood that y is going to indicate 2, 3, or 4 are those specific values. But let's look at it after the test. Excuse me, I'll reset this here in production team so that you can go back and cut that part out. I was talking over the flip of the page. So before we got the information here about the probability of y before the test has been enacted. What's the likelihood that we're going to end up with 2, 3, or 4? But let's ask a different question of after the test. Notice, by the way, I didn't really actually finally answer the question, what's the probability that the test is in error, that x is not equal to y. I'll let you work through that yourself. Okay. Here, after a test, now that one's been conducted, we observe that y is equal to 2, and now we want to have an updated probability mass function of x. Right, and we can take a look at now the conditional that of, really, this is what we're doing, the probability of the different x values given that y is equal to 2. So we're looking for 3 specific values here. And right now I've just represented as dashes for x equal to 2, x equal to 3, and x equal to 4, given that we've observed a test result. And these are called posterior results, after the test. Right? And really this is an application of Bayes' theorem, that we can look at this as the probability of x given y is equal to 2 is equal to the probability of our x value taking on a specific value and y equaling 2 normalized over the space that y was equal to 2. So for x equaling 2, then we know that the joint was equal to 0.21, that's what we found before, and then divide by the marginal of y, we have then a 0.33, and then we divide through and we get 0.67. Right, and so now we have an updated value for the PMF of x given what we just observed, which is more typically what we have in practice, right? We have some theory ahead of time, some prior knowledge, but now we've gone and observed a test result, and we want to know, well, how likely was that? Okay, production team, got a correction to make here. So I'm going to redo this page, production team, and because I made a numerical mistake, and I think it's better just to redo the whole little segment there, but it's tied to all this rest. So I'm going to pause it while I reset, and you'll have to cut out this whole page here. Okay, so we just came up with the joint probability masses associated with combinations of x and y, true strength versus observed strength, and we have now a new marginal set of y's before a test has occurred. What's the likelihood that we're going to observe a test result from the core of the cylinder of 2, 3, and 4 being these three probabilities? Okay, because I know what's going to happen here shortly, just keep this 0.21 number in mind for the outcome of x equal to 2 and y equal to 2. And that's because now we've gone and conducted a test, and so we've observed from that test that our core had a compressive strength of 2 ksi. And now we want to know, well, what's the new probability mass function of x given what we just observed? Or another way to write that is, what's the probability of x given that we've just observed a specific value? And we have three still outcomes for 2, 3, and 4. And this is what you would call the posterior probabilities, because they've happened after testing. Right, so we had a marginal value for x based upon prior history. That was before testing occurred. Now we've done some testing, and now we have a conditional distribution at work. That's different than the conditional distribution that we were working with before. And this is really just a straightforward application of Bayes' theorem. And remember that in Bayes' theorem, or in that model, we said that the conditional distribution could be thought of as the joint of x equaling a specific value and our conditioning event, in this case y equal to 2, normalized by that probability that y was equal to 2. Right? Remember I said to keep track of couple of numbers there before. That joint, that when, let's take a look at x equaling to 2, and for a specific case here. Joint of x equaling 2 and y equaling 2 was 0.21, and the marginal of y was 0.33. And divide those through, and we get 0.64, 64% chance. Right. And if we fill this on out, we have 0 here and 0.36 within rounding for those others. Okay. And so you might say, isn't there a circular argument going on here? Didn't we have to use some information before to have that? Well, yeah, we did. And that's why it's called the prior probabilities. And now we've had a test and we're updating what these new probabilities are. And that's different than what we had before. So presumably we have more information, so therefore our new information should also, our consequent information should be a little bit better than it was before. And of course you could go ahead and do this for more outcomes and continually update things as you go along, right? We had imperfect knowledge before, and now we have improved knowledge. And again, this is really coming out of Bayesian theory. It's really just another example or extension of what we were talking about before.